Welcome to Saitechinfo channel, my dear students. In this tutorial, let us discuss about Davisson Germer electron diffraction arrangement. Here, you got the electron gun where there is a filament F that is heated by a low voltage battery. So the electrons are ejected from the heated element and passing through a collimator as a collimated electron beam, and in fact it is accelerated by the high voltage battery. By changing the resistance of the rheostat, we can get the required potential so that we can accelerate the electron beam. So the A is the collimator, and through which the collimated electron beam is made to fall on the nickel crystal, the surface of the nickel crystal. Here the target of the electron beam is nickel. When it is made to fall, it gets diffracted. So the electron beam is scattered and it is diffracted. This diffracted electron beam is captured on the movable collector. By changing its position, we can detect it. And the detected signals are converted into current, and that is sensed through the galvanometer. So the entire setup is kept in a vacuum chamber. So this is the overall setup of Davisson Germer electron diffraction arrangement. The electrons here scattered in all directions by the atoms of the crystal. The intensity of the scattered electron beam, that is measured by the detector, as we already discussed. That detector can be moved on a circular scale so that the positions can be monitored. And the detector is connected to a sensitive galvanometer, so the impulses, the current is recorded here. The deflection of the galvanometer is proportional to the intensity of the electron beam entering the collector. The apparatus entirely, it is kept in an evacuated chamber. As I already mentioned, the detector can be moved on a circular scale, so the positions can be monitored, and the angle, the intensity, the scattered angle, that is the angle of scattering between the incident and the scattered electron beams can be found out by the circular scale. The variation of the intensity of the scattered electrons with the angle of scattering obtained for different accelerating voltages. Let me say, the voltage can be generally accelerated in the range 44 volt to 68 volt. Strong peaks are obtained for 54 volts at 50-degree scattering angle. The peak due to such constructive interference is possible due to the electrons are passing through the different layers of the crystal, and that's why they get diffracted. So the wavelength obtained, the wavelength of the matter wave was obtained in this experimental setup, that is a Davisson Germer, was found to be 0.165 nanometer. Now let us work out the de Broglie equation. According to de Broglie, lambda is equal to h by p, where p is the momentum, that is mv, and this can be interpreted for electron as, by substituting the value of this, can be illustrated as h by mv also. So by substituting the values, we can get what? For electron, that we already discussed, lambda E for the electron wave of E electron is equal to 1.227 divided by the whole square root of the voltage applied for the acceleration. So such nanometer. Now at 54 volt, so taking square root, now we are able to get 0.167 nanometer. So the striking fact here is the value obtained, the hypothetical value or the value obtained by the de Broglie hypothesis was found to be, as I already known, lambda is equal to 0.167 nanometer is found to be very closer to the wavelength of matter waves from the Davisson Germer experiment, that is 0.6165 nanometer. So Germer experiment confirms the wave nature of electron, and there is a relation de Broglie that is further validated here. We should try to understand the de Broglie hypothesis and its importance. In fact, de Broglie's hypothesis was the basic for the development of quantum mechanics. This has also led to the field of electron optics, where we were able to design electron microscope with very high resolutions. So the higher resolution, the resolution of electron microscope is much higher than that of optical microscope. With the help of this electron microscope, we were able to explore the micro world. So de Broglie has a major role in the modern quantum mechanics. So thank you very much for watching this video.